Hello, my name is Vin Sharma. I'm the engineering leader for the Amazon SageMaker Neo service. It's a new service that we launched at reInvent 2018, just a few months ago, and it's my pleasure to talk to you about what its capabilities are and how you can use it to deploy machine learning models everywhere. So if you're working with applications today that use machine learning models, you probably already understand how difficult it is to build, train, and deploy those models on various types of platforms. But what we'd like to do is make that really easy for you. And this was the design and intent behind SageMaker Neo. So without further ado, let me kind of dive into what the capabilities are, and we'll walk through it systematically. Our broad overview here is that we wanted to, as AWS, provide a capability that allows application developers and builders who come to the AWS platform to be able to create applications that are smart, devices that are smart, and to infuse those devices and applications with machine learning models that have been built with the data sets that are already in many cases resident on the AWS infrastructure, and these are large data sets that provide training examples to build these models. But the challenge typically in our experience with customers has been that we find developing and then tuning those models for deployment is a black art in and of itself. And so for applications where those models have to be deployed at the edge on devices like autonomous vehicles or tractors, or for industrial equipment that requires some amount of predictive maintenance, where you want to be able to tell if the transformer or the compressor is about to fail in a couple of months and send the field technicians in advance to fix it. Or drones or robots, any of those applications, we find that the devices that are deployed in the field tend to have certainly compute capabilities and some storage capabilities, but they're definitely not as powerful and robust as a server class machine in the data center, with which we in AWS are very familiar. So our challenge here is to be able to help developers build these applications and deploy them on a variety of devices. And if you look at the way that process works today, it is as complicated as it sounds. You start out with bringing your own algorithm to train the model, um, or you can very easily consume or take advantage of existing algorithms and models that we in the SageMaker platform provide. But in either case, you then have to construct a model, build a model that you can then train with the data that you bring to it. So in this case, the training examples can be a large set of images, or perhaps video streams, or speech or audio recordings of various kinds. And the model then learns to predict or make the predictions that you'd like it to make based on that training data. And then you are ready to deploy it in the field on devices or in um, EC2 instances that are set up to handle large streams of data or large volumes of data. But before you get to that point of deploying it to the cloud or to the edge, there is this optional step of optimizing the model. And that can be, in many cases, overlooked because it's difficult to do. And sometimes the results aren't necessarily promising. You could look at trying to optimize one of these large complicated models and deploy them onto the edge, but your results depend in large measure on the nature of the platform, the nature of the model, the hardware architecture, the skills of the developers, and the time that you have to exercise those skills. And so when you do make the change and you deploy it to the cloud or to the edge device and you test it frequently, when the time comes for you to then upgrade the model because the predictions aren't as high quality or as high accuracy you'd like it to be, then you're forced to redo this entire process, starting with retraining the model and improving its accuracy. So this is a complicated, difficult process, and we see a lot of customers in some ways held back from deploying machine learning on the edge at scale because of the complexity of this process. And so we started to talks specifically with customers asking what were some of the reasons why some of the reasons why these models are difficult to deploy. And what we've found as we look across the landscape of the state-of-the-art models that are trained for high accuracy or deployed on various devices is that there's a trade-off to be made. Models that are typically highly accurate have a number of parameters in them. They're very complicated differential equations that have been composed together to form a deep learning model. And there are many, many layers of the neural network that constitute this deep learning model, which makes the size of the model significantly large. And with that comes the need for consuming large amounts of memory on the device. And with it comes also the need for a significant amount of compute power on the device, neither one of which may be easily available. And this makes the models slower because they are accurate, but now you don't have the hardware or the platform capability to execute these models really fast. The other issue that we found that's really critical, and it's interesting and it's somewhat overlooked, is that the models today, whether they're machine learning models or deep learning models specifically, are trained in a framework. The framework provides building blocks. There are operators, functions, a library of tools and utilities and other components and capabilities that make it really easy to construct the model and take advantage in many cases of the fact that this is an open source framework. Others are contributing to it. Things are moving very fast, and you can build on the strengths of the platform, the framework itself. This is great when the time is when you're training the model. However, when the time comes to deploy the model, you have to bring the framework to wherever you deploy the model. It means that what happens in the framework has to stay in the framework, if you will. You're in some ways wedded. The model is wedded to the framework in which it was developed. It's a little bit like creating a Java program in a IDE, a development environment, and having to bring the entire development environment to the device on which you want to run the Java app or applet. And so we found that this tends to slow down the deployment quite a bit because now not only do you have a large model, but you also have the entirety of the framework that you have to fit onto the device. In some cases, the framework could be up to 1 gigabyte in size, and it could consume twice as much or 4 times as much memory. So this already limits the scale and the scope of the models that you can deploy on the edge. So this then brings the need for expertise. You want to be able to have the ability to tune the models and compress them and optimize them for the platform. You want to be able to kind of reduce the footprint of the framework itself. But to do all this, you need to understand not only the application development, whether it's in the cloud or on an embedded system, but you need skills in machine learning, being able to train the model and tune the parameters. You need performance, troubleshooting, and optimization skills. You need an understanding fairly deep of the frameworks themselves. Whether you chose TensorFlow or MXNet, you need to understand the framework. And then you have to figure out how to squeeze and fit that model and the framework onto a specific server class machine or an edge device. And that often takes a fairly deep today understanding of the underlying system architecture, whether it's RISC or x86 or some of the newest instructions available in either the Intel CPUs or the ARM processors, or the tensor cores that are available in the latest NVIDIA GPUs. And all of this takes time, which isn't always in abundant supply. So when we looked at the way development and deployment of machine learning models happens in practice today, we find this many-to-many problem where every framework has to be mapped in some ways to some of the most popular hardware from the processor vendors and devices based on that processor. And there's a lot of optimization that has to happen in the framework itself with libraries that are provided by the hardware vendors for each of these frameworks that take advantage of the underlying processor compute capabilities and deliver the best performance. At the same time, you want to be able to take the model in each of these frameworks, test and validate with each of these hardware platforms. So this many-to-many problem is the heart of what we want to solve. And that's where we started to rethink the way inference or machine learning models in deployment function today and what we could do to improve it. And that led us to creating the SageMaker Neo service as part of the SageMaker platform, specifically focused on that phase between when the model is trained and when the model is deployed, and specifically occupies the spot where you want to have the model that has been trained and it's now available for you to deploy, but you don't want to tune it for each platform as a separate task every time that you have to deploy that model. And so what we're looking for is a facility and a capability that lets you train once and run anywhere. And the way we do this is to kind of think of it as a way to build on an age-old computer science, computer engineering capability called a compiler. This compiler takes a program that's written in one language and converts it to execute on a variety of different target hardware. And it does that by mapping the program into increasingly abstract structures of computation that it can then optimize and then tune for the specific hardware. So we decided to take this approach and adopt this approach that's been that is actively being researched today in various academic as well as industrial research centers, and make that into a commercial production grade enterprise quality service. So think of this Amazon SageMaker Neo as a compilation service that allows models that are expressed in MXNet or TensorFlow or PyTorch languages, framework-specific formats, to be converted into a framework-agnostic format, an intermediate representation of that model, if you will, that you can then optimize and convert and tune for specific targets. In this case, we work closely with the hardware processor vendors and our partners to make sure that we are collaborating with them in delivering the best performance for these models in each of these frameworks. And when we do that, the model is now portable. It's been liberated in some sense from the framework, and it's now available to run on a variety of targets. And all you need is a single compact runtime on which the model can execute. You no longer need the framework. The runtime in this case takes the place of the framework. Where a framework could be up to a gigabyte or 600 megabytes, the runtime is less than a megabyte or close to a megabyte. And so the footprint is significantly smaller than it would have been if you had used the framework. And the performance is significantly higher than if you had simply run the model in the framework on that device, because we've done a number of optimizations in the process of converting it for that target platform. So that's the heart of it. And the way we do this is to kind of think of it much like any other compiler in the past. You have the ability to parse a model, which means in this case, we convert a model from its source format, TensorFlow, MXNet, PyTorch, or in our case, XGBoost, which allows us to capture decision tree models like random forests and various other trees, and convert them into a common format, into an intermediate representation. We then use a variety of techniques that come from the history of compilers, but also take advantage of our knowledge of deep learning models and machine learning models to optimize that computation graph, that structure of the model itself, to detect patterns in the model structure, and I'll talk a little bit about the nature of those patterns, but to be able to identify ways in which we can compress, condense, or in some ways optimize the computation graph. Then there's the business of being able to deal with the data as it flows through the computation graph. Imagine if you have a neural network with 152 layers, with a lot of crosslinks and connections. There's a lot of data the arrays, the tensors that flow through the neural network layers are constantly being converted, reshaped. And when we look at the layout transformations of these tensors, there are ways in which we could reduce the number of conversions and optimize the execution time. And finally, when we now have a representation that retains the accuracy of the original model but is now faster in execution time, we pass that on to a low-level code generator that creates the executable for the target platform. And we take advantage of the best that level of components provide to us, either from open source or from the platform, the processor partners with whom we work. So if you look specifically at the nature of these optimizations, some of the things that we do at the graph level involve pruning the graph, being able to identify nodes that are that may have been necessary during the training phase but are no longer necessary for inference of the model for when it is running in production. Fewer feedback loops, if you will, being able to do layout transforms, fuse some of these operations and functions that happen consistently together. So if you find a pattern of nodes in the graph that are continuously replicated or repeated, then we have ways in which we can fuse them into a single operator and map that single operator to a low-level function or set of low-level functions in the platform-specific code. And then when you look at the nature of the tensor optimizations of the data layout optimizations, it involves being able to chunk the data into a size that can be consumed and processed by the underlying platform hardware, being able to take advantage of the underlying instructions, the instructions in the instruction set of the hardware platform specifically that allow for vectorization in various kinds of operations at a much larger block of data than individual elements or components. So all of this becomes then available when you look at the complexity of what we're doing here. We want to fundamentally treat that as the heavy lifting that we do, and we want to help you as a customer avoid having to do all that. So we simplify the experience of consuming or using this optimization capability by creating a very simple user interface. All it takes is to be able to come to the AWS console, invoke the Amazon SageMaker service, and within the SageMaker console you would see right around here where it talks about where we have links to inference capabilities, a compilation job that you can then kick off. And the compilation job really requires very little input from the user. In this case, all we're looking for is the model, the location of the model on an S3 bucket that you own, the name and shape of the input node. In this case, is fairly simple to express as a JSON in a JSON format, and the nature of the framework itself. So it could be MXNet or TensorFlow or PyTorch or Onyx, and the location of the output where you want the model that's then compiled and transformed to be deposited. So you can then pick that up. So in this case, more often than not, it's the same S3 bucket in which the original model sits. And then finally, the target platform. You could choose a variety of targets. In this case, most of the instances that are available under the SageMaker hosting capability for deployment. In this case, it could be ML, C5, C4, M4, M5, P3, and P2, so CPU-backed as well as GPU-backed instances. And you click submit, and within a minute, typically, in less than 5 in most cases, we compile the model and return it back to the S3 bucket from which it was originally retrieved. I'm going to pause here and talk a little bit about how you might use this even more easily than with the console that I just showed you, because we've developed a number of notebooks. So these are Python notebooks, Jupyter notebooks that you can very quickly instantiate, deploy in a hosted SageMaker notebook instance, and invoke and deploy. And I'll give you a quick example of one where it kind of demonstrates the capability of this compilation function in the context of an existing Jupyter notebook. And so in this case, let's look at a model that performs image classification. And this is, to get to this, all you have to do is, you could kind of search for the SageMaker Neo documentation on the AWS site, and you'll see links to various sample notebooks that you can then quickly customize. So you'll see at the bottom here a number of these notebooks, and we're going to pick the one that says model optimization with an image classification example. So if you were to go to the notebooks, you'll find that you could pick any one of these, but the one that we're going to try to execute here is going to be the image classification with both training as well as the Neo compilation function inside it. When you click and run it, you'll notice that it has a number of functions that are already built in for you to extend or modify, and it's very easy to simply execute it as is, and you get a sense of the benefits of the compilation as well as the original execution and inference. So I'll explain as we go further, but the gist of it is that you have a notebook where I'm going to skip a number of these steps that actually take a long time to set up, because most of the time is consumed in instantiating the containers and the instances, and that's not relevant to this conversation. I'll focus primarily on the compilation process and the execution time, but I do want to set the context for this. So I'll show you what that looks like. So there's a bunch of sections of the notebook here that involve setting up the environment variables and the permissions for the account, preparing the data, downloading the data set from its original location into the S3 bucket, from which you can then use it to train the model. And so that's fundamentally what's going on there. And then the time comes for you to actually execute the training job itself. Here you're retrieving the data set from its S3 location using the SageMaker training function to execute the training job on a P3 8x large GPU-backed instance. You can complete the training with the hyperparameters set for that particular training job. And in this case, we've set the epochs really low, so the accuracy is likely to be very low. But that said, you get the gist of the task here, which is to train the model. Once the training job is complete, you'll see sort of output that looks like a series of epochs being executed with the accuracy being validated at each stage. Eventually, when you've terminated the job, the training job completes and you've got a trained model. So at this point, most often today, the default is for you to then execute this model in the framework, run it directly in the framework. And to do that, you take the model and you deploy an instance on EC2 under SageMaker hosting, where the hosting capability allows you to scale the instances and the number of nodes on which you can execute the machine learning model that you've just trained. And you can test this in this notebook. We've downloaded a sample image with which to test it, and you kind of imagine that this is the test image that's rendered. What we want to do is evaluate it. So I'm going to show you just what the time to execution looks like for the model when you're running it within this instance. If it's 10 invocations of the API to execute the model, it took about 580 milliseconds, and these times can vary, so we can kind of try to do it a couple of times. And you'll see that the accuracy is what it is. We haven't really done a whole lot to train the model for a very long time, so the accuracy is not relevant here, but it is a constant. It's preserved when we run it through the Neo compilation process. So let's look at what happens when you run it through Neo. And in this case, we want to optimize the model. So in this case, you're just selecting the location of the model, invoking the optimization functions, and now you have an optimized model that you can deploy, much like you did the original model. So we're giving it a different name for the deployment instance and executing it on a C5, different target than the one on which it was trained, so you can deploy it wherever. And again, if you look at the execution time, this is now 333 milliseconds. It could be slightly different, lower as you get execute faster. And so what we're going to do is um, on average, if you look at the inference latency before it was optimized, it's about 545 milliseconds to after it has been optimized, it's about 260. So on average, when we look across a variety of image classification models, in this case, whether it was ResNet or VGG, Inception, AlexNet, or DenseNet, SqueezeNet, MobileNet, we find that the performance of the model is optimized up to 2x the original execution time of the model in the framework on whatever platform we've tested. So we've tested across all of the platforms that you see here supported in SageMaker Neo. And that's the end of the notebook, and then it sort of cleans up the instance so you're not wasting resources, and that's pretty much all there is to it. So in a nutshell, what we see SageMaker Neo is a capability that allows you to get the same accuracy of the model that you've trained the model for, but now with the ability to port it, so you get the portability of having it run on a variety of different platforms, and you get better performance. And the optimizations that are done are not manual and painstaking as they used to be, but are simply almost one click with the touch of an API or a button. And we support a variety of frameworks and a variety of platforms, with new platforms coming soon as we partner with processor vendors to make sure that we're extracting the best performance from each of their hardware devices and accelerators. As a follow-on to this, one of the things that we are very passionate about is making sure that we acknowledge the sources of the capability. We've worked very closely with open source communities, specifically TVM, developed by the Paul Allen School of Computer Science and Engineering at the University of Washington, as well as TreeLight, which is another open source project that compiles decision tree models. Our team has contributed and is an active member of the open source projects and contributes upstream to the community and works within the community of both of these projects. And at the same time, all the modifications that we've made as part of creating this capability as a cloud service, we're returning, in some sense, contributing back to the open source projects. And we're doing this in two ways. One is to be able to take the compiler-specific optimizations, all the graph optimizations and the tensor optimizations I spoke of earlier, and make sure that they're part of, as much as they can be, within the philosophy of the community that drives the open source projects, that they're upstreamed into the original TVM and TreeLight projects. At the same time, we have made a number of things that make the deployment of the model on a single compact runtime that handles both decision tree models as well as deep learning models. And so we want the runtime to be to have that unified and simplified API that lets you very quickly deploy and invoke predictions from the model on both cloud instances as well as edge devices. And that runtime is its own project, and we're making that available as part of the GitHub Neo AI and repositories, which allows device makers to very quickly customize it. So within a week after we released it to open source, we've seen that runtime be ported to Windows platforms, interestingly, as well as a variety of other devices and architectures. And so this is exactly what we'd like to see, is the community build a variety of modifications and customizations to the runtime. So it allows machine learning models that are compiled, whether they're compiled with the open source TVM compiler or Treelight compiler or the Amazon SageMaker Neo service, to be deployed wherever the runtime can be installed, and which in our mind ought to be everywhere. And so there are a number of ways in which contributors can participate in the GitHub project in the organization. We have a structure that allows contributions from processor vendors as well as device makers to make both the compiler as well as the runtime more extensible, and for this to be a framework that suggests a broader reach for a wider range of models and architectures. So we'll look forward to working with our partners, and you should see a lot of updates rapidly in that community. And with that, thank you for your time and attention, and I'm happy to take questions.